Now that we understand implicit differentiation and how to pay attention to the variable of differentiation, we can solve related rates problems, which means I can take some function that is area in terms of radius, and I can differentiate with respect to a different variable such as time. So I can find the rate at which the radius or the area is changing over time. All right? So we're going to draw a picture, always drawing a picture, and name the variables and the constants. We're going to use t for time, and we'll assume that all variables are differentiable functions of t. We want to make sure that we, write down our numerical information and make sure we're using the symbols that we've chosen, the variables. And then we want to determine what we need to find, which is usually a rate, and that's going to be a derivative. So the hard part here is we need to write our equation, and sometimes we may need to combine two or more equations to get a single equation that relates the variable whose rate you want to the variable whose rates you know. And then the big thing here is we're going to differentiate with respect to t. So again, we might have a function in terms of x and y, and we're going to take the derivative with respect to t. Or, and it could be some other variable, it's just t is what we most commonly use. And then at the end, once we have our derivative, and remember a derivative represents a rate of change, then we can evaluate what we're dealing with. So one thing, we might do is find how fast a ladder is sliding down a wall. And if we think about a ladder sliding down a wall, that's a vertical rate. So we might represent that with dy, vertical change over time. Or how fast an area is changing. So if we had some equation, area in terms of a distance, x or y, that area, rate of change, might be the derivative of area with respect to time. So we just really want to make sure we're paying attention to what the variables are and what we want to differentiate with respect to. So we're going to do a problem here. We're not putting any application or context to the problem. We just have a function, 2x plus 3y equals 12. It's in terms of x and y. We have information about dy dt, and in an application setting, this might represent a vertical rate of change. And we're being asked to find dx dt, which could represent a horizontal rate of change. So the function's in terms of x and y, and we need to differentiate with respect to t. Okay? Is there a t in the given equation? And the answer is no. So when we differentiate a different variable like x with respect to t, we're going to need to write dx dt behind it. So in order for me to solve this problem, I'm going to take the derivative with respect to t of 2x plus 3y equals 12. So I'll differentiate each term with respect to t. So I've got d dt of, I'm going to have 2x in here, plus d dt of 3y equals d dt of 12. So I've got each term, 2x, 3y, and 12. The derivative of 2x becomes 2, and I took the derivative of x, so I write dx dt. The derivative of 3y is 3, and in this case I took the derivative of y with respect to t, so I write dy dt. And then the derivative of 12 is 0. Okay? So we're done with our derivative. Now we know that dy dt is -2, and we're asked to determine what dx dt is. So at this point, it's just we're going to be plugging in values that we know, or rates or constants that were given inside the application problem. So if I plug in -2 for dy dt, I've got 2 dx dt plus 3 times -2 equals 0. Well, that's a -6 equals 0 there. So that's a -6. When I subtract it, I've got 2 dx dt equals +6, and dividing by 2 on both sides, I determine that dx dt equals 3. So I can find a value. And then again, if this had context, x might represent horizontal change over time and y a vertical change over time. So this could be like feet per second or miles per hour. But we don't have a context here. So basically we're going to be dealing with some pretty simplistic equations and then applying this related rate derivative knowledge to those basic equations. So here we have another example, and this problem has context. So this gives us an idea of more what we're going to see in this section. So we're dealing with a hot air balloon which is rising straight up from a level field, and it's tracked by a rangefinder which is 150 meters from the liftoff point. At the moment, the rangefinder's elevation angle is exactly pi/4, which is 45 degrees. We know the angle's rate of change, the angle is increasing at a rate of 0.14 radians per minute. And so we want to determine how fast the balloon is rising at that specific moment. So when we talk about a moment, we're talking about right when we know this information. Because as that balloon rises, the angle changes. Okay, and if you think about, this angle increasing as it's moving, as that balloon goes up, it starts to move at a slower rate of change as it gets up higher, right? And so try to visualize, put your arms straight out to the side, and as it rises, as you're tracking that balloon, as it gets higher in the air and your arm rises, eventually it would start to rise a little bit slower. And so what we're going to do here is we're going to develop equations so that we can set this up. And I've given us this picture from the text that we're dealing with. So we would draw a picture thinking about what we're looking at. And so this rangefinder, 150 meters away, is looking at this balloon rising up. We have some given data that represents our moment. And we are talking about the rate at which that angle is changing. So draw the picture on your paper. And think about what your variables are and list them in a way that makes sense to you. And then think about what you're being asked to find. We're being asked to find how fast the balloon is rising. So that's a vertical rate of change. And I might think about this. This says find dy dt at the moment when we know the angle. So the angle we might call theta. At the moment when theta is pi/4 and the rate at which that angle is changing, so that would be d theta dt. So we'd have 0.14 radians per minute. So what I've written in green here, this part that I've circled, this is at the specific moment, and that's data I'm not going to use till I get to the end of the problem. But looking at what I have here, I've got y's and thetas. So y and theta, I'm going to differentiate with respect to t. I need to figure out how to relate y and theta. And if I come over and I look at my picture, I've created a right triangle. So in this situation, we might want to use some right triangle trig. So if I wanted to relate that angle to that side, and I'm dealing with an angle, I know this 150 is never going to change. And then this y value will change. What I can say here is that tangent of theta, remember tangent is opposite over adjacent, is y over 150. So now I have an equation that relates theta and y. And I'm going to take this equation and I'm going to differentiate with respect to t. So differentiating our tangent equation with respect to t, the derivative of tangent is secant squared. So I have secant squared theta, and I took the derivative of theta. So I write d theta dt. And the derivative with respect to t of y over 150, and keep in mind y over 150, that's the same as 1 over 150y. So that derivative is just going to become 1 over 150. And I took the derivative of y, so I write dy dt. So this is my rate of change, my derivative equation. And I'm being asked to find dy dt. And I know two pieces of information. I know theta and d theta dt. So if I plug those two values in, secant squared of pi over 4 times d theta dt, which is 0.14, that equals 150 dy dt. And so I only have one variable here to isolate. So at this point, it's just a matter of solving this equation for dy dt. So I'm going to multiply by 150, and I've got 150 secant squared of pi over 4 times 0.14 is dy dt. Now, secant of pi over 4, secant is reciprocal to cosine. Cosine at pi over 4 is root 2 over 2. Cosine pi over 4 is root 2 over 2. So that means secant of pi over 4 is 2 over root 2, which rationalizes and just becomes root 2. So I have 150. Secant of pi over 4 is the square root of 2, and because it's squared, I put that there. And 0.14 dy dt. So root 2 squared becomes 2. 2 times 150 is 300 times that 0.14. And 300 times 0.14 is 42. So I determine here that 42 equals dy dt. And so this is a y with respect to t. So y is my vertical distance changing over time. So when we state our answer here, it is 42, and my units on distance are meters. My unit on time is minutes. And I get that from, looking at the values initially established in the problem. And then you'll say to yourself, well, I know it is rising because it's positive. So it's rising at 42 meters per minute at that exact moment. When the rangefinder is looking at the balloon and it is at a 45-degree angle of elevation off the horizon, the balloon's rate of change vertically is 42 meters per minute.